In this video, I'd like to do a very brief proof of law of sines and why it works using basic definitions of sine, actually. That's why it's law of sines. We work with sine here. So let's suppose we have some triangle. We'll do a quick sketch of this. We're not looking for anything beautiful or perfect. And let's just call this A, B, and C. If I were to draw an altitude into this triangle, now remember, an altitude is the height of the triangle with a perpendicular intersection of the opposite side here. And the altitude, we're just going to call that h. H is pretty typical for this because of height. It'd be nice to use little a, but we are going to be using little a here to parallel this other side. And we'll call this little b and call this little c. Now, I'm going to only prove one pair of things here because you're going to see hopefully that this can be extrapolated to the other combinations of sides and angles. What I want to do is focus on the two angles that are part of these two smaller right triangles here. So A and C, they're both parts of these little right triangles that I've created. Angle B, I'm going to ignore for now. That means little b is going to get ignored as well. So for this one, we're going to prove the iteration where little a over sine of big A equals little c over sine of big C, or vice versa, whichever way it ends up turning out for us. So what I'm going to do is go, well, look, we need to talk about sine of big A. That's part of this whole process. And I already said I was going to talk about sine of big C as well. So I just want to remember back to SOHCAHTOA. I know that sine is always the opposite side of my right triangle from my angle divided by my hypotenuse. So for sine of angle A, if I go to the opposite side in the triangle, that's the height h, and our hypotenuse is little c. That means that sine of big A is just h over c. And what I really like is that sine of c is very similar, except it would be h over little a. Well, my formula for law of sines does not include h, so we're going to get that out of here somehow. And I see that both of these equations have an h to be solved for. So let's try that out. We're going to multiply both sides by these denominators. So I'm going to put c up here by multiplying both sides by little c. And over here, I'll multiply both sides by little a. Maybe I'll go back to my convention from previous videos of putting a little hat over big C, just so I know that it's not the same as little c. But what I know now is that all of these things here must be equal, because C sine of A and A sine of big C are both equal to h. Well, h is obviously equal to h, so that means that these two things must be equal to each other. So I'm going to write that out. And so when I look at that, I go, okay, that's not how law of sines looks, but we can sort of think about the opposite of cross multiplication. We can kind of pull this back apart. In fact, by understanding cross multiplication, you should agree that one of these two things must be true. And this is not pulling apart one side here. This is just me saying I have two ways to look at how I could break this up. I could divide both sides by little c and little a, and I would get sine of A over little a equals sine of C over little c, or I could divide both sides by sine of big A and sine of big C, and instead I would get c over sine of big C equals little a over sine of big A. Either version of this should look very familiar now. Obviously, I've left out sine of big B and little b, but that's because this is set up to prove the relationship between A and C. If I were to go back and redraw a triangle with a different altitude, then I could compare B and C in the same way. So this is very doable to go ahead and show the other route. So I won't do that here because I think that's fairly intuitive. Remember that variables are interchangeable, so this would be very simple to go ahead and tack B into this as well. And there you go. That's the proof of law of sines.